Hello and welcome to the course on rock mechanics principles. In the previous parts, we have covered mechanics of rock materials, properties of rock joints, and classifications of rock masses. To understand those properties and to obtain the parameters describing the mechanics, laboratory experiments and measurements are often conducted. Part 5 is to learn the methods and the techniques on rock mechanics testing. In Part 5, we will cover tests and the measurements on rock materials and rock joints. For rock materials, we will cover density, porosity, water content, swelling index, durability index, rock surface hardness, sonic wave velocity in rock materials, uniaxial and triaxial compressive strengths, Brazilian tensile tests, and point load strength tests. Tests and the measurements on rock joints include joint shear strength and the normal stiffness tests, measurements of orientation, frequency, and RQD. It also covers the techniques of using hemispherical projection to present and to analyze joints. All those tests and measurements covered in Part 5 are common rock mechanics tests on rock materials and rock joints. They are supplement materials to the subject covered in Parts 2 and 3. Therefore, Part 5 should be studied in parallel with Parts 2 and 3. For example, when you are learning Section 2.2, Mechanical Properties on the Compression, which covers uniaxial and triaxial compressive stresses, you will need to study Section 5.3 on uniaxial and triaxial compression tests. Let's start with the measurements of the basic physical properties such as density, porosity, and water content of rock materials. The International Society for Rock Mechanics and Rock Engineering, ISRM, has produced a number of suggested methods for rock mechanics testing and measurements. We will use those ISRM suggested methods as guidelines for the tests described here. For measurements of rock material density, porosity, and water content, we will use the ISM suggested method for determining water content, porosity, density, absorption, and related properties, and the swelling and the slack durability index properties as the reference. We will need to determine mass and the volume in order to calculate density. Dry mass is the mass of solid only, here denoted as MS. It is the mass of rock materials when it is completely dry. To make sure it is completely dry, rock sample is dried in a ventilated drying oven for at a temperature of 105 degrees C for a period of at least 24 hours. The temperature needed to be maintained at 105 degrees C within plus and minus 3 degrees C. The sample is then measured every 4 hours until the change in mass is less than 0.1%. Then the rock sample is considered as completely dried sample. The mass measured at this condition is the dry mass or mass of solid. Saturated mass is the mass of the rock material when it is completely saturated with water. That is when the voids in the rock materials are filled with water. To achieve this status, rock sample is immersed in water in a vacuum saturation equipment under a vacuum of about or slightly less than 800 bar for a period of at least 1 hour. Again, we need to measure a few times to make sure that the mass becomes constant and the rock is completely saturated. The mass measured then is the saturated mass. Determining rock sample volume is easy if the sample is of regular shape. In most cases, for testing samples, they come in regular shapes, often as circular cylinders cut from cores, or cube, or rectangular cylinders. For regular shape, we will use vernier or micrometer caliper to measure the dimensions, such as the diameter and the length. Those tools usually have accuracy of 0.1 millimeter to micrometers. With the dimensions measured, we can calculate the volume using the standard volume equations. For example, for circular cylinder, the volume is the area times the length, which is 1/4 pi d square times L. Or for cube or rectangular cylinder, it is the width times height times length. For irregular shape, for example, a lamp block, we can use Archimedes' buoyancy principle to measure the volume. This is done by measuring the weight of a saturated sample and the weight of saturated sample when it is submerged in water. The difference between the two weights is the weight of the water of the same volume of the sample. Since we know the density of water is 1000 kilogram per cubic meter, we can calculate the volume. The accuracy of mass measurements should be 0.1 grand. With mass and volume measurements, we can compute density. With the measurements on dry mass, saturated mass, and saturated submerged mass, we can also determine the volume of void and the volume of water in the sample. The difference in the masses between fully saturated and dry samples is the mass of water in the void. Again, divided by the water density, we can obtain the volume of the water fully occupying the void. And hence, it is the volume of the void. Again, we need to keep the accuracy of mass measurements to be 0.1 gram. Water volume at any wet condition can be determined by measuring weight between wet and dry samples. Accuracy to 0.1 gram and calculate the volume. This is to determine the water content or degree of saturation. We can calculate density, porosity, and water content related physical quantities. Equations are shown here. For example, total density of saturated or wet samples is given by the total mass divided by the total volume of the rock sample. Dry density is the dry mass divided by the total volume. Porosity is the ratio of void volume to the total volume. A porosity of 0% means there is no void at all. When porosity is 20%, it means 20% of the sample volume is a void, and the solid occupies 80%. The void may be occupied by air or by water, fully or partially saturated. Water content represents the amount of water mass in sample, and it is the ratio of water mass to solid mass. Degree of saturation represents the percentage of void filled by water. So it is the ratio of water volume to void volume. 100% saturation means all the void are filled by water. Test report should include descriptions of the sample, rock type, location, how sample is collected and stored, the initial or natural water content, color photos of the specimen should be attached. It should also include how the specimen volume is determined. For regular shapes, measurements on dimensions should be recorded. For irregular shapes, mass measurements on saturated and submerged specimen should be recorded. All the measurements should be presented in tabulated form. Typically, there should be at least 3 specimens per rock sample for the measurement. calculate the bulk and the dry densities, porosity, water content, and saturation degree should be presented in tabulated form. Density should be given to the nearest 10 kg per cubic meter, and the porosity to the nearest 0.1%. Now we come to section 5.1b. In this section, we will learn how to perform swelling tests. We will cover unconfined free swelling and confined swelling. Unconfined swelling is to measure how much the rock will swell or expand when it is saturated in water for a long period. The test results are given as a swelling strain. Confined swelling is to measure how much force the rock will be produced during the swelling when it is saturated in the water. The test results are indicated by swelling pressure. We will follow the ISM suggested test methods on swelling tests. The methods are outlined in the two ISM suggested test method documents. One is the suggested method for determining water content, porosity, density, absorption, and related properties, and the swelling and the selectability index property of 1977. And the other one is the suggested method for laboratory testing of swelling rocks of 1999. Unconfined swelling or free swelling is the expansion of rock material in water without any confinement. It is basically done by submerge the rock specimen in water and measure the deformation. There are two types of apparatus available for unconfined swelling tests. One is shown on the up figure. It consists of a cubic box, typically made of plexiglass with open top. The box is mounted with micrometer dive gauges or LVDTs on four sides to measure the lateral swelling deformation. The axial swelling deformation is measured by another micrometer dive gauge or LVDT fixed on the top. The specimen can be a cube or a circular short cylinder. The apparatus in the lower figure uses a flexible ring with rubber band and a measuring device wrapped around the circular specimen to measure the circumferential swelling deformation. It has also a glass plate to be on top of the specimen to measure axial swelling. The specimen should be, in this case, circular short cylinder. To start with the tests, we need to prepare the test by cutting the rock sample into the test specimen of suitable size and shape. With the core samples, it will be easier to cut the cores to short lengths to approximately equal to the diameter. For block samples, you can cut the specimen into cube. Please take care of any anisotropy. If possible, cut the rock so that anisotropy plane parallel to vertical or horizontal. Minimum dimension of the specimen is 15 mm or 10 times the maximum grain in the rock specimen. Typically, specimen size of 50 mm or more is preferred. If you have an apparatus of mentioned by ISM in 1977, you place the specimen in the center of the container box, adjust the 4 lateral macro die gauge point to touching the specimen sides in the middle, and the axial die gauge points touching the specimen on the top central point. Make sure all the gauges are smoothly functioning. If you have the apparatus suggested by the ISM in 1999, you first put flexible ring assembly along the specimen circumference. The flexible ring consists of elastic rubber band and a flexible steel band with calibrated displacement measurements to 0.1 mm accuracy. Place the specimen and the ring assembly into the center of the container and the glass plate on the top of the specimen. Adjust the axial gauge point touching the glass plate in the center. Now you are ready to start with the test and the measurements. By adding water into the container and until the specimen is fully submerged in water. Throughout the test, you may need to add water to make sure the specimen is always flooded by water. Always take the reading on the die gauges or LVDTs before watering, and then after watering, take readings regularly and continuously at time intervals and record them. They are the swelling deformations. Stop the tests until all readings reaching constants. Unconfined swelling strain is defined as a swelling displacement divided by the original length. Swelling strains are calculated for axial, lateral, or circumferential measurements. Unconfined swelling strain in axial direction is therefore calculated as measured maximum axial swelling deformation divided by the specimen length in axial direction. Lateral swelling strains in 2 perpendicular horizontal directions can also be computed in the same way as lateral maximum swelling displacement divided by the original length or diameter if circular cylinder is used. For tests using flexible rim band, the displacement measured is the circumferential displacement, and therefore is divided by the circumference of the circular cylindrical disc. It is almost as a standard requirement that test report should include descriptions of the sample, log type, location, how sample is collected and stored, the initial or natural water content, and color photos of the specimen and the test setup with apparatus. Typically, there should be at least 3 specimens per log sample for the measurement. Tabulated values of specimen dimensions, swelling, displacement readings from the micro gauges or LVDTs, calculated unconfined swelling strains and their directions with respect to bedding or foliation orientations, and descriptions of any visible deteriorations of the specimens. In underground situations, rocks are subjected to confinement and confining stresses. This is why we need to do tests to measure swelling characteristics under confined condition. Apparatus for confined swelling includes a radial confining metal ring cell with open top. The specimen is fitted inside the ring, and the radial swelling is therefore limited by the metal ring. Porous plates are on the top and at the bottom of the specimen for allowing water seeping through to the specimen. Micrometer dye gauges or LVDTs are used to measure axial swelling displacement while the specimen is loaded by axial loading device. The apparatus also includes a container to hold water and the specimen. The confined swelling test apparatus is illustrated on the right. As the specimen should be confined, therefore, we need to prepare the specimen in circular disc form to be fit in the metal ring, or to fabricate the metal ring to fit the disc. Either way, the metal ring must be fitting the disc specimen. Specimen should have diameter at least 38 mm. Most likely, specimens are cut from rock cores, and therefore its diameter D is around 50 mm. The height T of the circular disc should be less than 0.4 of the diameter. The minimum thickness is 15 mm or 10 times the maximum grain diameter of the specimen. The specimen is placed inside the metal ring with porous plates at the bottom and on the top. The specimen assembly is placed in the container covered with steel loading plate. The whole assembly is then placed under the axial loading system with axial loading gauge or LVDTs attached to the steel loading plate. After the test assembly is completed, a small axial load is applied to a surcharge pressure of 5 to 10 kilopascal. The container is then filled with water to submerge the specimen with water to cover the top porous plate. Now we are ready to record readings on swelling displacement and axial load. For confined swelling tests, we want to determine the stress that limiting swelling, called swelling pressure index. Increase and adjust regularly the applied axial load to maintain zero swelling. If swelling displacement is positive, we increase the axial load. We may need to decrease the axial load if the displacement becomes negative. Through regulating the axial load, we want to keep the thickness of the specimen to be within 0.01 millimeter of the original thickness. That is, we are maintaining or to limiting any swelling in the axial direction. Finally, we will find an axial load to stabilize the swelling displacement. Maintain that axial load to ensure that swelling displacement remaining at zero for a while before ending the test. Readings of swelling displacements and axial load should be recorded regularly. As we mentioned before, the unconfined swelling test is to determine the swelling pressure index, which is the limiting stress to stop rock from swelling. From the test data, this swelling pressure index is the axial load applied in the test to maintain zero swelling displacement divided by the cross-section area of the specimen. That is the equation here. P swell equal to F divided by A. Report of confined swelling test is very similar to the report of unconfined swelling test. They should include the descriptions of the sample, log type, location, sample collection and storage, the initial and or natural water content, and color photos of the specimen and the test setup with apparatus. Again, there should be at least 3 specimens per rock samples for the measurements. Recorded data and the measurements include the measurements of specimen dimensions, tabulated readings of swelling displacement, and axial load. Test results are the calculated swelling pressure index and their directions with respect to bedding or foliation orientation, and also descriptions of any visible deteriorations of the specimens. We are now coming to the tests on durability of rock material. The test we conduct is called slick durability test. Slick durability test is designed to simulate physical weathering through drying, wetting, and physical contacting, and to measure the resistance to such weathering processes. Again, we can find the suggested method on testing slick durability by the International Society for Rock Mechanics, and we will follow the ISIM suggested method, learn how to conduct the slick durability test. The main apparatus for the slick durability test is the slick durability drum assembly, as shown below. The available slick durability system usually has 2 drums of 140 mm diameter made of steel mesh of 2 mm mesh size. The drums can be rotated by a motor at 20 revolutions per minute. The drums are partially submerged in water. The dimension of the drums are specified in the ISM suggested method. Other apparatus needed are an oven can have temperature controlled at 105 degrees C to dry the specimens, and a weighing device with accuracy of 0.5 gram. Test procedure starts with sample preparation. For each sample, the rock needs to be broken into small pieces of lamps. Each lamp should be between 40 to 60 grams. Corners of the rock lamps should be rounded. For each slick durability test, we need 10 small pieces of lamp. The total weight of the 10 lamps together should be 450 to 550 grams. Specimens are placed inside a clean drum. The drum and the specimens are put in the oven at 105 degrees C temperature for 2 to 6 hours. The rock specimens are dried. The total mass of the specimen and the drum is measured by the weighing balance and is recorded as mass A. The drum with rock lamps specimens attached to the slake deliverability apparatus. The water tanks are filled with tap water at room temperature, typically at 20 degrees C, to the level at 20 mm below the drum axis, or 50 mm above the drum bottom. Now the drum is partially in water and the rock lamps are fully submerged in the water. Switch on the motor and rotate the drum and let the drum rotate for 200 revolutions or 10 minutes. Remember, the rotational speed is 20 per minute. After the drum and the rock lamp have rotated in water for 10 minutes, turn off the motor, detach the drum from the slake deliverability apparatus, and the drum with rock specimen are then put in the oven again at 105 degrees C for another 2 to 6 hours. The rock specimen in the drums are again dried. The total mass of the specimen and the drum is measured and recorded as mass B. We'll repeat the steps for rotating the drums and the rocks for the second round for another 10 minutes, and then dry the rock with the drum again in the oven for another 2 to 6 hours. When the rock lamps are dried, we again measure the mass of the drum with rock lamps inside, and it is recorded as mass C, which is the mass after 2 rounds of rotating in water and drying. The final step is to remove the rock specimens from the drum, brush the drum clean without any fragments inside, and weight the drum. Record the net weight of the drum as mass D. Slake deliverability index is usually calculated for 2 cycles of slake deliverability tests. The slake deliverability index is the ratio of the final to initial masses of the rock specimens after the test. It can be computed from the mass measurements recorded from the deliverability test. Slake deliverability index of 2 cycles, ID2, is equal to C minus D, which is the dry mass of the rock specimen remaining inside the drum after the 2 test cycle, to be divided by A minus D, which is the original dry mass of the rock specimens put into the drum before test. The calculation is shown by the first equation here. However, for poor, weak, or highly weathered rocks, they are not durable In the test, rock lamps of those rocks may not be able to sustain 2 rounds of rotating in water and drying. That is, after the second round, there is very little or even no rocks remaining in the drum. Therefore, ID2 is close to 0. In the case of ID2 is below 10%, we will use the one-cycle selectability index, ID1, which is calculated as B minus D divided by A minus D in percentage, shown by the second equation here. Here, B minus D is the dry mass of the rock specimen after the first test cycle. The test report should include descriptions of sample, rock type, location, sample collection and storage, and how specimens of small lamps are prepared, the initial or natural water content. Typically, there should be at least 3 tests to be conducted per rock sample. The report certainly will present the recorded measurements taken during the test and the computed 2-cycle stability index to the nearest 0.1%. If the 2-cycle selectability index from a test is lower than 10%, you also need to calculate and report the 1-cycle selectability index to the nearest 0.1%. Information on testing, including information on slaking water, source, and the temperature. For example, tap water of 20 degrees C. Any abnormal performance of selectability apparatus should also be reported, such as vibration, inconsistency in rotation speed. Descriptions of fragments retained in the drums and the materials passing through the drum should also be reported and ideally photographed. Photographs of original samples, prepared specimen before testing, retained fragments in the drum, and the passing materials in the water should also be attached in the report. This is the end of session 5.1 on density, porosity, water content, swelling, and the durability. Thank you, and see you at the next session.